Okay. Welcome all. I am Nimai Bairagya, Assistant Professor from Agriculture Engineering Department, Haldia Institute of Technology. So today I discuss a topic about vapor compression refrigeration system. So vapor compression refrigeration system is a refrigeration system which is basically used for food preservation as well as household refrigeration or commercial refrigeration. So coming to the slide. So here is the content. First we discuss about introduction, then component of vapor compression system. Next, the vapor compression cycle, different diagram of VCRS and COP of VCRS, some example of wood refrigerant, and at the end, the application of vapor compression system. So in next slide. Okay. Vapor compression system is a mechanical refrigeration system which is use a liquid refrigerant. So the refrigerant is working as the changing its phase. So why need of changing its phase? Because by the compression and the expansion, the refrigerant is extract heat when it's in the after the expansion in the evaporator, and the refrigerant is reject heat in the condenser. So by these main two components, by compression and expansion, the main refrigeration system is work. So in the next slide. Okay, before going to the vapor compression refrigeration system, some related term, very important related terms is we have to know. First one is superheating. So superheating is the defined as the heating a vapor above its boiling point. So here is the superheat condition. So here is the superheat condition where the vapor is applied heat above its boiling point. So if we need an example of water, so when we apply heat in the water vapor above the 100 degrees Celsius, because the boiling point of water is 100 degrees Celsius. So this condition is known as the superheating condition. Next, subcooling condition. So this is the subcool condition. So subcool condition is basically the removing of heat from a liquid or liquid vapor mixer below its condensing point. So subcool liquid may be pure liquid or maybe liquid vapor mixer. Then another is saturation. So saturation is two types. First one is total vapor, saturated vapor or pure vapor, and second one is pure liquid or saturated liquid. So when the saturated, we talk about the saturated liquid. That means here 100% liquids, 100% in the mixer is 100% liquid. There is no gas or no vapor is present. But when the 100%, when you talk about the saturated vapor, that means there is no presence of liquid. That means 100% vapor is present there. So as well, 99% vapor and 1% liquid, that may also be considered as the pure vapor or saturated vapor. Another 99% liquid or 1% vapor, that also considered as the pure liquid or saturated liquid. So in next slide. So previously talk about the phase change. So how the phase change is happened in the refrigeration system. So here a graphical presentation. In the y-axis is temperature and in x-axis is energy. We consider as heat. So if we consider water for the phase change purpose, so here I mentioned the temperature. Let the temperature is starting from minus 20 degree. Next minus 10 degree. Next 0 degree. next 20 degree, 30 degree, next 100 degree, next maybe 120 degree or 130 degree. So these are all in Celsius. So if we see that in the starting point, if we consider minus 20 degree Celsius, here the water is in solid form. So the water is in solid form means that is ice or crystallized. So the ice, when we increase the temperature, as we in the y-axis we denoted the temperature. So when we increase the temperature at the 0 degree Celsius temperature, it is start melting. That means it is converting in water. That's is the position of starting the phase change. That's why this position is the phase change position. So here is temperature is not rising. Here only a heat is working, that is latent heat. So latent heat. So in the changing of phase, the heat is working, that is latent heat. In next position, after when the total solid ice is melting and converted into total water, then if we again rising the temperature, then it continue 30 degree, 40 degree, and when it comes to the 100 degree Celsius, then it start again changing its phase. That is in vaporization. So this position also latent heat is working. Latent heat is working, and this position the total water is vaporized and change its phase. That's in vapor. So here one is a vapor change position, and here another is vapor changing position. So when the water or when the solid ice is changing its phase, that's time latent heat, that is a heat that working on this time. So as we applied heat, increasing the temperature, that is only increase the temperature, but when it's come to the changing its phase, we need the latent heat. So at the first position for the melting of ice, that first latent heat is working. Second, when the water is vaporized, this time also latent heat is working. So basically this mechanism is working for every fluid for the changing of its phase. So in vapor compression refrigeration system, there is main 4 components. First one is compressor, second one is condenser, third one is expansion valve, and fourth one is evaporator. So compressor, what is compressor? So compressor, the system is as known as a compression. So compressor. So compressor is a mechanism that when the vapor or vapor is incoming or entering in the compressor chamber, it is compressed, and the temperature as well the pressure is increased. So and it is converted into the superheated vapor. So it is the main mechanism of the compressor. Second is condenser. When the superheated vapor is come to the condenser, so in the condenser chamber, it is a mechanism that the superheated vapor is reject heat in the condenser, and it is change its phase and it is converted into liquid. So the main mechanism of the condenser is the superheated vapor is converted to liquid. Next one is expansion device. When the subcooled liquid enters in the expansion valve, so when the expansion valve is open, the sudden or rapid fall of pressure, that's why a huge temperature drop is happened here. That's why cold or K8 is here, temperature is very low and pressure also here K8 is very low. That's why the expansion valve is open and the liquid is converted into liquid vapor mixer or only vapor, and which temperature is very low and pressure also is very low. This is the working of expansion. Next, evaporator. So evaporator is mainly working as absorb its heat from its surrounding. So when the liquid vapor mixer or the vapor is conveyed to the evaporator works as its absorb heat from its surrounding, and the vapor is the liquid is converted into vapor and conveyed to the next position. So this force cycle is repeatedly going on, and the vapor compression system is going on. So here is compression. So compressor, what the position of compressor in the diagram, schematic diagram of vapor compression system. Here is the compressor. So compressor is previously we said here is a suction valve and here is a discharge valve. So after the evaporator, exit of the evaporator, the vapor, the low temperature and low pressure vapor is entered in the compressor. So low temperature and low pressure. So low temperature, low pressure vapor is enters into the compressor, and here a piston is present here. So this piston start working and the gas is compressed. So gas is compressed and exit as high temperature and high pressure. So when it is exit, it is as high temperature and high pressure. So this is the mechanism of compression which we use in the vapor compression system, and it is the position of the compressor after the evaporator and before the condenser. So remember it. Next. So next is condenser. So position of the condenser is here after the compressor. So what is the mechanism of condenser? So previously we said that condenser is convert the vapor into liquid. Basic working principle of the condenser. So how it is work? So it is the entrance of the condenser. So which is after the exit of the compressor, the vapor is entered into this position. So when the high temperature and saturated superheated vapor, so superheated vapor when the superheated vapor enters into the condenser chamber, it is start liquefying or it is changing its phase. So changing its phase and the vapor is converted into liquid. So here is the exit point of the condenser. So the liquid sample refrigerant is exit from this exit point. So for the liquefying purpose, we use the cooling water or any other things. It is the entrance point, and hot water is come out from this position. For the cooling the high temperature superheated gas. So by the cooling, the superheated high temperature gas is converted into liquid, subcooled liquid. So this is the working of the condenser. So next is the expansion valve. So this is the position of the expansion valve. So what is the main working principle of the expansion valve? So after the exit of the condenser, there is the liquid form of the refrigerant. So when the liquid and subcooled refrigerant is enters into the expansion valve, and the expansion valve is sudden opened. So by its sudden opening, the temperature as well the pressure is dropped, and by for the pressure drop, the temperature drop also created, and the temperature is very low in the exit position of the expansion valve, and pressure also very low. So here is the diagram of the expansion valve. So it is the entrance point of the expansion valve. After the condensed liquid, it is enters through this port, and by the sudden opening of this valve, it is created the pressure drop and the temperature drop, and exit through this towards the evaporator. So this is the main working of the expansion valve, to create the pressure drop as well the temperature drop by the sudden opening of this valve. So next is the evaporator. So evaporator is mainly working as it absorbs heat from the surrounding of its. So this is the position of the evaporator. Okay, so if we talk about the household air conditioning system, the inner part which is in the indoor position, that part is the evaporator in the air conditioning system. So the working of the evaporator. So after the exit of the expansion valve, the refrigerant liquid vapor mixer is enters in this position and convey through this bare tube. When it is conveying through this bare tube, it simultaneously absorbs the heat from its surrounding. If we keep here some food material or some ice cream, some vegetable, or any atmosphere of the room, it start absorbing heat. Because low temperature fluid is conveying through this bare tube, and by the adjacent temperature is very low also, and by this tube, this is a metal tube. Remember that this is a metal tube, copper tube mainly used. That's why it absorbs the heat from the surroundings, and the liquid vapor mixer, the liquid vapor refrigerant is converted into vapor, only pure vapor, and exit through this. This is the exit position. This is the enter position. This is the exit position. So this is the working of the evaporator, that is absorbing the heat from its surrounding and convert the liquid vapor mixer into the pure vapor refrigerant. Okay, so in the next slide, so it is the schematic diagram of the vapor compression refrigeration system. So previously I told that in the compressor, after the exit of the evaporator, the saturated vapor is entered into the compressor and it is compressed by the compressor. So for the compressing purpose, we have to work done on it, that is equal to m into h2 minus h1. So what is h1? So h is denoted by the enthalpy. So in the number 1 position, that is denoted by h1, enthalpy 1, and number 2 position, that is denoted by h2, enthalpy 2. Similarly, it is h3, enthalpy 3, and it is h4, enthalpy 4. So by the work done, m into h2 minus h1, the vapor refrigerant is compressed and it's conveyed to the condenser. Here condenser, which I previously told, condenser is ejected heat, that is Q out, that is m into h2 minus h3, that means h2 minus h3, because h2 is greater than, h2 is always greater than h3, because here it is ejected heat and then it's conveyed to here, so h2 is always greater than. Next, it's conveyed to the expansion valve. So in the expansion valve, in this line, H3 is equal to H4, because here it is the same enthalpy line, that's why H3 is equal to H4. So for the sudden opening of the expansion valve, the liquid refrigerant is converted into the liquid vapor mixer, and then it conveyed to the evaporator. In the evaporator, it absorbs heat from the surrounding, and the liquid vapor mixer is converted into pure vapor and conveyed to the next compression. So this cycle is repeatedly work done, and the vapor compression refrigeration cycle is repeatedly done. So in the next slide, okay, it is the pH diagram of the vapor compression refrigeration system. So if we want to establish a diagram of P for pressure, and H for enthalpy, so in the x-axis enthalpy, in the y-axis pressure, so we can see that 1 to 2 is the isentropic compression. Isentropic compression. So 1, 2. So this is the compression position. So 1 to 2 is the isentropic compression. So what happened here? Here we said that pressure is increasing. So this is the pressure in y-axis. So pressure is increasing. Okay, that is justified. Next, 2 to 3. What happened? 2 to 3, heat is rejected, but in same pressure. So we respect to the pressure. So pressure is constant in the 2 to 3. So that's why 2 to 3 pressure is constant. Okay, that also justified. Next, 3 to 4. What happened? In 3 to 4, sudden opening of this valve, pressure drop and temperature drop is created. So here we talk about the pressure. So pressure drop, sudden opening, and then rapid pressure drop is done here. So 3 to 4 is the pressure is decreasing. You can see here. Next, 4 to 1 is the evaporator work. So what happened in evaporator? Evaporator is also the done at the constant pressure. So pressure is also as the same. So 4 to 1 is also the pressure is constant. So this is the constant pressure. This is the constant pressure. Okay. So 2 to 3 is known as the isentropic refrigeration, because condenser is rejecting heat. 3 to 4 is the isentropic expansion, because here expansion work is done, and 4 to 1 is the isobaric heat addition. Heat addition because evaporator is absorbing heat. Okay, in the next slide. So refrigerating effect. So for this total refrigeration cycle, what we need, why we using this system? For the refrigeration purpose. So that is known as the refrigerating effect. So refrigerating effect is equal to Q is equal to H1 minus H4. In the previous slide, we can see here is the evaporator, and I told that it is in the indoor position where we need the refrigeration. So 4 to 1, this position is the refrigeration position. So refrigeration effect also act here. So that's why refrigeration effect is equal to H1 minus H4. That is equal to enthalpy at one position minus H1 minus H4. Refrigeration effect I can write as RE. So H1 minus H4. H1 that is one position enthalpy and 4 is equal to 4 position enthalpy. So it is a RE. So the unit of refrigeration. So the unit of generally we use the ton refrigeration. You hear this word ton in household purpose or commercial purpose. The 1 ton air conditioning system, 2 ton air conditioning system, or 1.5 ton air conditioning system. So what is ton? So ton is basically defined as 1 ton of ice. The amount of heat needed to melting the 1 ton of ice to 1 ton of water in 24 hours. So the total amount of heat needed is 3.516 kilowatt. So it is a TS diagram. Previously we see the PV diagram. Here we see about the TS diagram. TS means temperature and S means entropy. So what happened here? So similarly, from the 1 to 2 position, here compression work is done here. So with respect to temperature, so what happened in compressor? The temperature is rising, right? Okay. So in the graph, we can see that 1 to 2 that temperature in y-axis, so temperature is increasing, right? Okay. 2 to 3, what happened here? Heat is rejected. That means heat is decreasing. So here 2 to 3 condition, heat is decreasing some portion because heat is rejected here. Next, in the 3 to 4 expansion, so 3 to 4, here expansion valve is open and temperature drop is created. So we talk about temperature here, respect to the temperature drop is done here, and so this is the decreasing of temperature. And 4 to 1 is evaporator work is done. That means in constant pressure, evaporator is absorbing the heat from the surrounding. So this is the 4 to 1. So in the next slide, okay. So we talk about work done in previously in compressor. We done work to run compressor work. So here some external work has been done. So what amount of work has been done here? So we can see that work done is WC, as it works in the compressor. That's why C is denoted here. So WC is equal to H2 minus H1. So H2, that is here H2 and H1. So compression work done is enthalpy H2 minus enthalpy H1. So this position is done as the compressor work. This is H2, this is H1. So compressor work WC is equal to H2 minus H1. So this is the compression work done here to run the system. Okay. Now we calculate the COP. COP means coefficient of performance. So what performance is done the refrigeration system, we can measure by calculating its COP. So previously we see that compressor work is done here. That is WC is equal to H2 minus H1, and refrigeration effect, where is it? We can refrigeration effect is done here. So refrigeration effect we can denote it as RE. We previously showed that refrigeration effect is enthalpy at one position minus enthalpy at four positions. That is H1 minus H4. So clearly we see that in the graph, if we done work at in the compressor, that is H2 minus H1, we can output result as refrigeration effect RE, that is H1 minus H4. So COP means refrigeration effect by work done. That means QC, that is QE, because refrigeration effect done in the evaporator, that's why it is denoted as QE, and work done is denoted at WC as it is works in the compression. That's why refrigeration effect QE, that is E, also known as, and work done WC. So RE is equal to H1 minus H4, H1 minus H4, and work done is equal to H2 minus H1, H2 minus H1. So this is the equation of COP. This is a very important equation for calculation the numerical problem in vapor compression refrigeration system. So you have to remember this equation. What is COP? COP is equal to H1 minus H4 by H2 minus H1. So coming to the next slide. So here is some advantage of vapor compression refrigeration cycle. So firstly, it is smaller size compared to the other refrigeration system. This is the advantage. Second one, it has less running cost. When we running this system, its running cost is very less. Third one is coefficient of performance is quite high compared to the other refrigeration system. These are the advantages of this system. Some disadvantage also here. The disadvantage is the initial cost is very high to establish this vapor compression system, and second one is the leakage of refrigerant in vapor compression system is major problem. So some desirable characteristic of good refrigerant. So here the refrigerant will be non-poisonous firstly, non-flammable, low boiling point, and suitable to latent heat and low specific volume. These are some good characteristics of refrigerant. Some thermodynamic properties of refrigerant. Some good thermodynamic properties of good refrigerant actually, because there are many refrigerant is available, but some good refrigerant have some good thermodynamics property. That should boiling point should be very low at atmospheric pressure, and freezing point should be also very low. And lagging load should be high. That is working in the changing of the phase from liquid to vapor or solid to liquid. So this latent heat, so it should be high of the refrigerant which we can use. Specific heat is low for liquid and high for vapor, and specific volume is low for vapor. So these are the features for a good refrigerant in and thermodynamic property. So here are some example of good refrigerant. First one is R11, R12, R22, R717, R134A. So from this, most low temperature refrigerant is R22 because it can create minus 40.8 degrees Celsius. So in the commercial purpose, for the commercial food storage, for a cold storage, so this when temperature is needed very low for the ice cream manufacturing factory, that we can use the R22 as refrigerant because here the temperature is it can keep the temperature very low, minus 40.8 degrees Celsius compared to the other refrigerant. Okay, next the application of vapor compression refrigeration system. So application household refrigerator which we use in the household purpose, that we can use the vapor compression refrigeration system. Next, residential building or shopping mall. In the residential building or shopping mall, where we use the centralized air conditioning system, where we can use also the vapor compression refrigeration system. And in the automobile air conditioning purpose, we can also use vapor compression refrigeration cycle. So here is a numerical. So we try to solve it, simple numerical. So here a R12 vapor compression refrigeration system operates at discharge temperature is 40 degrees Celsius and suction temperature is minus 5 degrees Celsius and develops 25 tons of refrigeration. Calculate the refrigeration effect, mass flow rate and COP of the system. So here from the refrigeration property table, some data is given here. H1, H2, H3. So first of all, to solve the numerical, we have to draw the graph, PS diagram. So that is H1, this is H2, H3, H4. Okay, so we know that COP is equal to refrigeration effect, that is H1 minus H4 by work done, that is H2 minus H1. So first we have to calculate the H1 minus H4, that is H1 is 185.35 minus H4. So here you can see that H4 data is not available. So in previous slide I said that H3 is equal to H4 because it is lied in the same enthalpy line. So H3 is equal to H4 because it is as the same enthalpy line. Minus, so H4 is equal to 74.59 by H2 minus H1, that is 207.14 minus H1 is 185.35. So if we calculate this, it is approximately come out as 5.08. and it is unitless because it is the fraction of two components. So COP will be 5.08 approximately. And we have to also calculate the COP is calculated refrigeration effect. So refrigeration effect is simple, H1 minus H4. So this will be your refrigeration effect. So RE is equal to we can write this. So this will be R is equal to maybe 110. So RE is equal to 110.15 kg. Approximately RE refrigeration effect will be H1 minus H4, that is H1 and that is H4, and after calculating this will be your refrigeration effect RE. And another one is mass flow rate. The formula of mass flow rate is equal to M is equal to Q by RE. Q means total heat. Total heat of the system is 1 ton is equal to, we know that 3.5 kilowatt. Here 25 ton. So 25 into 3.5 by refrigeration effect is 110.15 something. So if we calculate, the mass flow rate is equal to fractional maybe 0.89 kg per. This is approximately. If we calculate this, maybe this will become so, and unit will be in kg per minute. So you can see that we from this numerical problem, firstly we calculate the COP, next the refrigeration effect RE, and the mass flow rate, that is M is equal to Q by RE. So this will be very helpful for your examination. These types of numerical problem is come in your examination. So you have to practice this, and further more complicated numerical will be there in your book. So you have to practice this. So thank you for your time. I hope you have learned something from this video lecture. Okay, thank you.